This video is going to be on partial fraction, decomposition, and telescoping series. The rule that we're going to be working with is the fact that if you have a sum to infinity of b sub n minus b sub n plus 1, there's going to be terms farther down that cancel out previous terms. And once you take the limit of the general equation, once you've plugged in everything, if it's finite, then the series converges and the sum is the first term minus the limit. So the first example we're looking at is the sum from n equals 1 to infinity of 2 over 4n squared minus 1. I'm going to rewrite that as the sum from n equals 1 to infinity of 2 over 2n minus 1 and 2n plus 1. Now this right here is a partial fraction decomposition, so what you have to do is you have to make it a over 2n minus 1 plus b over 2n plus 1, and then take the cross, so cross multiply and solve for a and b. Once you figure all that out, you should get that the final sum from 1 to infinity, it's going to be 1 over 2n minus 1 plus 1 over 2n plus 1. Now what I'm going to start doing is just plugging in terms. So for n equals 1, we're going to have 1 over 1 plus 1 over 3. That's n equals 1. I'm going to add that to, so n equals 2 then is going to be 1 over 3 plus 1 over 5. Now as you can see, the 1 over 3 and then the this actually should be a minus 1 over 2n plus 1, so that becomes a minus. So now as you can see, the 1 over 3 subtract if you subtract 1 over 3 from 1 over 3, those are going to cancel out. So those terms cancel out and you're going to be left with, so I'm going to write my general equation as the sum from 1 to infinity, or you don't have to write that, but you can just write it as 1 minus 1 over 2n plus 1. The very last step you have to do is take the limit of this. So if I take the limit as n approaches infinity of 1 minus 1 over 2n plus 1, this term, the denominator is going to go to infinity, so that's going to equal 0, and you're going to be left with 1. And since that's a finite value, that this sum converges. So that's that one. And now we're going to go to a little bit less difficult problem, but this is your jungle trial 2 number 1. And for this one, I'm just going to immediately start plugging in terms. So if I plug in a 2, I'm going to have 1 over ln of 3 minus 1 over ln of 2. So that's for n equals 2. And I'm going to add that to n equals 3, which is 1 over ln of 4 minus 1 over ln of 3. And so I just keep adding, so I'm going to do maybe one more. So n equals 4, I'm going to have 1 over ln of 5 minus 1 over ln of 4. And now you can see that the 1 over ln of 3 and this 1 over ln of 3 cancel out. So I'm just going to cancel those two out. What else cancels? The ln of 4's cancel. So what you're going to be left with, the general equation is going to be negative 1 over ln of 2. And this term right here, so if you see the 1 over ln of 5, we're getting that, since it's the first part of it, it's going to come from this first part of the equation. So I'm just going to add a 1 over ln of k plus 1. And that's the generic formula. So maybe I should write that off to the side. Generic formula. And you're going to need that because and then what you do is you finally, once again, you take the limit. So this would be k approaching infinity of negative 1 over ln of 2 plus 1 over ln of k plus 1. And once again, the denominator is going to go to infinity, so that's going to be 0. And you're going to be left with negative 1 over ln of 2. And since that's a finite value, once again, this series converges. And that's it for telescoping series and partial sums. And a quick thing I want to mention is when we talked about the sum over here, we said it's the first term minus the limit. But if you look at this example number 2, the first term cancels out. So the sum for this one would have to be different, and it would just actually be this negative 1 over ln of 2, which is the second term, because the first term canceled out. So that sum rule only applies if the first term does not cancel.
Alright, hey there everybody, this is a video pretty much covering geometric series. And these aren't really complicated series, pretty easy to go through, and they have fairly simple rules. So the general formula for a geometric series is sigma a r n minus 1. And you have r as the common ratio and a is the first term. Now, to determine if a series converges or diverges, if the absolute value of r is greater than or equal to 1, the series diverges. And if the absolute value of r is less than 1, the series converges. Now, given that the series converges to a value which is equal to a over 1 minus r, where a is we already discussed the first term and r is the common ratio. Now we can go through examples to demonstrate this. Alright, so this isn't really in the series notation, but it's still a series nonetheless. 1/3, negative 1/6, 1/12, negative 1/24. So in this example, the first term a is equal to 1/3, and now I determine the ratio. Well, 1/6 divided by 1/3 is the common ratio ends up being 1/2, or negative 1/2. Sorry, it's my bad. So now, and the absolute value of negative 1/2 is less than 1, so we know that the series converges. So given that the series converges, now we can determine what does the series converge to. And so in order to do that, we use the formula we discussed. And let's just plug in some values. So the first term was 1/3, divided that by 1 plus 1/2. And you end up with a value of 2 nines. So that's the first example for a convergence. Sorry, the square is off. And so that's the first value, and this is a convergent series. So now let's go to the next one. This is also a geometric series with 3 to the n minus 1. And so for this one, to find a, just plug in 1 where the series starts. So 3, 1 minus 1 is equal to 3 to the 0, which is equal to 1. So that's your a. And r, we can see right here is 3. But since 3 is obviously greater than 1, greater than or equal to 1, the series diverges.
Hello, my name is Kroos for the purposes of this video. This is a quick tutorial on alternating series and absolute and conditional convergence. So there's some basic things we have to check if we can use the alternating series test. One, the series must be always positive, always decreasing, and the limit of a sub n as it approaches infinity must equal 0. So if you look right here, the test, when you're testing for positive decreasing and the limit, you ignore the alternation. As you can see, I've indicated right here, negative 1 to the n, negative 1 to the n plus 1, etc. And then also note here, I've rewritten these rules here in gray below, so you can see n plus 1 must be less than or equal to all n. And I put an asterisk for all n because if this isn't the case at first, you're looking as the function over time. So if the first couple terms don't follow this rule, it's okay if you know that this is the case over time. And then the limit as n approaches infinity of a sub n must equal 0. And this is also another note. This is a test of convergence. And this alternating series test does not indicate divergence. So I'm going to scroll down here. Absolute and conditional convergence. These are very much a part of alternating series. So both absolute and conditional alternating series converge. The difference being an absolutely convergent series converges regardless of the alternation or not. So a conditionally convergent series only converges with the alternation. So if you take the absolute value of the series, it will diverge. So here are two examples. So example 1, here's your function, and I circled it for you. I'm going to write out a couple terms just so we can see how the function or the series is behaving. So 1 would be the first term, minus a half plus a third minus a fourth, and so on. Pretty straightforward. You can see that if you ignore the alternation, the series is just simply 1 over n times -1 to the n minus 1. So we're looking at 1 over n when doing these three rules. So sorry for the scrolling issues. So it goes 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. So it's clearly positive, clearly decreasing, and the limit of 1 over n as n approaches infinity is in fact 0, so that checks out. So this is convergent because all the rules check out. So this is a convergent alternating series. However, if we check for conditional or absolute convergence, we know the series from n equals 1 to infinity of 1 over n is in fact a p series. So 1 over n to the p in this case equals 1. So because that denominator isn't decreasing fast enough, this is actually going to diverge the absolute value of a to the n, of a sub n. So this is only conditionally convergent. Okay, now for our next example. Okay, so if I write out the first couple of terms, you can see that if you ignore the -1 to the n, the series is just a geometric series of 1/3 to the n minus 1. And if we do our alternating series test, we can see that a n plus 1 is less than or equal to all a n. So if we take the absolute value of these, you can see that it's decreasing and positive, and that the limit of as n approaches infinity of 1/3 to the n minus 1 is 1 over infinity, so that equals 0. And now if we check, so it's convergent, and if we check for absolute or conditional convergence, we can take that 1/3 n minus 1, and it's a geometric series, and our R value is 1/3, which is in fact less than 1. So the absolute value of this series will also converge, so this is absolutely convergent.
Hi, we're going to go over the root test today. It's pretty simple. You have a series of the sum of a sub n, from going from 1 to infinity. You're going to take the limit of that series as n approaches infinity, but you're also going to take it to the root power So over here have it as the radical of n, which is also the same thing as putting it as the limit as n approaches infinity, a sub n, absolute value, that quantity to 1 over n, which is how I'll be writing it out. It's a little easier to see. And you're going to solve for L, and if L is less than 1, it's going to absolutely converge. If L is greater than 1, it's going to be divergent. And if L equals 1, we don't know what it is. It could be divergent, absolutely convergent, or conditionally convergent. So we have some examples to go over here. This first one is pretty simple. You have the sum as from n is 1 to infinity of the quantity 3n plus 1 over 5n plus 2 to the power of n. So you're just going to take 3n plus 7 over 5n minus 2 to n, absolute value that, and then take it to the 1 over n. So that 1 over n and this n right here are going to cancel out. So it's going to be 3n plus 7 over 5n minus 2. And since we're going to be taking the limit as n approaches infinity, it's going to be 3n plus 7 over 5n minus 2. This 7 and this negative 2 are not going to matter because this is going to be 3 infinity and 5 infinity. So as we approach infinity, the 7 and 2 will have a minimal effect. So that's just going to become the limit as n approaches infinity of 3n over 5n. And then you can cancel out those n's. So it's going to be, so this is L. So L is going to equal 3 over 5. And 3 over 5 is less than 1. So this is an absolutely convergent series. This next one gets a little trickier, but it's simple once you figure out how to isolate the power to n. So you might not think that you're going to use the root test here, but if you make it n to the n over 3, and you factor out an n, so n and then 1 over n plus 2, you do that, and then it's going to be n over 3 to the 1 over n plus 2, all that to the n. That is the same thing. And then you're going to just take that, I'm going to rewrite it so we have a little more room, 3 to the 1 over n plus 2, all to the n, absolute value, and then put 1 over n, that cancels. So now we have the limit as n approaches infinity of n over 3 to the 1 over n plus 2. Now once you have that, you're going to plug infinity in for n. So it's going to become n over 3, 1 over infinity. And that 1 over infinity is just going to become a 0. So you're going to have 3 squared. So it's going to be n over 9. And then plug infinity in for this n up here, because it's still the limit as n approaches infinity. It's going to be infinity over 9, which is just going to be infinity in the end. So L equals infinity, and infinity is obviously greater than 1. So this series is going to diverge.
Good afternoon, everybody. This is Blue Jay here, and I'm going to be talking about the ratio test today. Now, the premise behind the ratio test is that essentially we're taking two different values of the function, a of n plus 1 and a of n, and we're taking the limit of that ratio. And what a ratio is essentially a relationship between the former and the latter term. And in analyzing this relationship, we can find the behavior between them. And because this behavior is the same between every a of n plus 1 and every a of n, that relationship can, it gives us kind of a scope to what the end behavior of the function looks like. And so by analyzing the limit of n approaching infinity of the absolute value of a of n plus 1 over a of n, we get this idea of what the function is doing. Now over here you see a chart that designates what the different values of n correspond to. If we have an L less than 1, the series converges. An L greater than 1, the series diverges. And if L equals 1, we're not sure. And the reason that this is what it is you have to analyze what this actually means. Because if a of n is greater than if a of n plus 1 is greater than a of n, that means the series is slowly getting larger, and in that case, the series is going to diverge. If a of n plus 1 over a of n is less than 1, that means the terms are decreasing in value, which signals that the series is going to converge. And of course, if they're equal, then it could go either way, and we would have to perform another test. So let's begin by taking this quintessential problem here. We have negative 10 to the n divided by 4 to the 2n plus 1 times n plus 1. And now, as you see up here, we need to divide a of n plus 1 times a of n. Now, with complex problems like that, like this one, it can be difficult to do that kind of division. And so we want to tackle this problem in a more refined manner. So in that case, I'm separating a of n plus 1 over a of n into the reciprocal of a of n times a of n plus 1 over 1. So it looks like this. When you separate it like this and turn it into a multiplication problem rather than a division problem, it's easier to see how the terms cancel out and how to individually multiply the terms. So let's begin. First, we want to take 1 over a of n. So we're going to do the reciprocal of what we have right here. So we're going to write 4 to the 2n plus 1 times n plus 1, and divide that by negative 10 to the n. And all we did here was just take the reciprocal of our original equation, which is just a of n. And now the second part of our multiplication problem is to do a of n plus 1 over 1. So all we have to do is take this original equation and add 1 in all instances of n. So we're going to multiply this by negative 10 to the n plus 1, divided by, of course, 4 to the 2n plus 1. And remember, because it's going to be n plus 1, you get an extra 2, so it becomes 2n plus 3. And of course, our n plus 1 is getting an additional 1 due to the n plus 1 term, and so this becomes n plus 2. So this is the equation we have now, and this right here is all equal to this a of n plus 1 divided by a of n. And we'll put in the absolute value at the end. Really the only purpose of that is so that we get a whole number, a positive integer or fraction to use the limit comparison test. And so now we multiply this out, and I'll separate all the terms for you so it's easier to understand. Okay, so we have 4n plus 1 at the top right here, times n plus 1, and then times, of course, negative 10 to the n plus 1. On the bottom, we have negative 10 to the n times 4 to the 2n plus 3 times n plus 2. And so now that we have all of these terms together, it's much easier to cancel all of them out. So we can see here that we have negative 10 to the n and negative 10 to the n plus 1. This can cancel out, leaving simply negative 10 to the 1 on top. Over here, we have 4 to the 2n plus 1 and 4 to the 2n plus 3. These also cancel out, leaving simply 4 squared. Now we take what we have left and bring it down here to determine the final answer. So we have negative 10 times n plus 1 and divided by 4 squared times n plus 2. Now, with our definition of limits and knowledge from limits, we know that we can only need to look at the coefficients when this occurs. So when you multiply this out, you're going to get negative 10n minus 10, and then 16n plus 32. So when we only look at the largest exponent of n, we're going to get negative 10n over 16n. Now, when we find the limit of the absolute value of this function, we get 10 over 16. Now, going back to our original set of rules, we know that 10 over 16 is less than 1. Then thus, by the definition of the ratio test, we know that this series converges.